Welcome students. Welcome to the problem session 1. This problem session is designed particularly for these three topics: feedback principles, signal flow graphs, transient response. So this problem session is going to have questions from previous year's GATE examinations, IES examinations, and some of the questions were also asked in IAS examination also. We will be solving such questions, bunch of such questions which are simple, which are little tough and little tricky. I advise you that you take up a pen and a paper to solve all these questions, and whenever you see a problem, you try to solve that yourself. If you can, you should pause the video and try to complete the problem according to you. As you have learned the theory sessions, we will be using the same principles that we have studied in the theory sessions. If you have gone through all these concepts, it will be easy for you to do the problem. These problems are not very difficult. You should be able to solve them. Worry not if you are not able to solve that. I am here to solve all these questions for you. So we'll be taking up every problem from each topic and solving it thoroughly. We'll be having multiple choice. So we'll be choosing one of the options as a correct answer. I hope you have taken up your pen and paper so that we can start with this problem session 1. So we'll be going in order from the problems of feedback principles. Then we will go to the problems related to the signal flow graphs. Then we will see problems from transient response. Of course, because of the time limitations, we have not included every problem from these examinations, but we have chosen some of the important problems, and I'll be explaining you some concepts related to those problems so that you learn more while solving these problems. So let us start with problems related to feedback principles. Problem number 1. Despite the presence of negative feedback, control systems still have problems of instability because option A, components used have non-linearities. Option B, dynamic equations of the subsystems are not known exactly. Option C, mathematical analysis involves approximations. And option D, the system has a large negative phase angle at high frequencies. To solve this problem, let us go into the concept of negative feedback. We all know that negative feedback is nothing but the comparison of reference value and the feedback value coming from the output. So this is our output y of t and this is r of t. The question asks if there is the problem of instability because we have different components which possess non-linearity. Okay, so basically option B, which reads dynamic equations of the subsystems are not known exactly. So this is the case in a lot of systems. So be it a positive feedback, be it a negative feedback, if this should be a problem, this must be a problem in every kind of system. If you do not know the equations of subsystems exactly, this problem of instability should persist. So option B is not the answer. Option C reads that the mathematical analysis involves approximations. Yes, the mathematical analysis always involves approximations, be it any system. Again, not only for negative feedback, for any system having any kind of feedback and having different differential equations, mathematical assumptions are always done, but which is not actually the reason behind the instability. Because even the non-linear systems, when they are approximated, or some of the systems when they are approximated in mathematical systems, they work for certain range, and that is why there is no cause of instability originating from the assumptions. Option 4 reads that the system has large negative phase angle at high frequencies. Yes, even if you have a positive feedback, and even if you have negative feedback, the phase angle depends upon the poles and zeros of the characteristic equation, but which is not the main cause of instability. So option C and option D are also not the answer, because that we have the components that we use, they have non-linearities, and the main cause when the negative feedback is given is when there are non-linearities present. You do not have stable input. You cannot determine input according to your mathematical rules or according to the natural physical laws. You have to approximate your system uniquely, and you cannot generalize non-linear systems, and that is the main reason of instability in the system. Okay, so this is a theoretical question. So option A is correct in this question. Let us go forward and see problem number 2, which asks that with negative feedback in a closed loop control system, the system sensitivity to parameter variation, option A, increases, option B, decreases, becomes 0, or option D, becomes infinite. Now let us recall the function for sensitivity. So according to the function of sensitivity, S T G, which is given by dou T by T divided by dou G by G, where T is nothing but closed loop transfer function. Okay, and G is open loop transfer function, or rather any transfer function of the system, and G is considered as open loop transfer function. Okay, so for any system, the question asks if negative feedback is presented in a closed loop control system, the system sensitivity will. Now let us draw a system. Okay, so we have a certain parameter G, and then you have output when you give the reference input. Okay, you have feedback through block, let us say H, and which goes as a negative feedback. Now you know that the transfer function of such a system is given by G upon 1 plus GH. Okay, now you have the open loop transfer function, which is G. Open loop means you have to forget the negative feedback and just consider if there is only forward path through G, then the transfer function would be G. Okay, so this is open loop transfer function. Now sensitivity parameter for open loop system, if there was no feedback going through, so even my transfer function would be G for open loop, and there is no question of closed loop, so the sensitivity would be according to this equation. For T is equal to G, this would be 1. For open loop, it would be 1. Now this is the sensitivity for open loop system. Now let us calculate the sensitivity for closed loop system. We have to calculate dou t by t upon dou g by g, which gives dou t by dou g, g by t. Okay. So using t is equal to g upon 1 plus gh and g is equal to g, and differentiating this particular function with respect to g, you will get 1 upon 1 plus gh as your answer for sensitivity for closed loop. Okay. So now for open loop, the sensitivity was 1. Okay. And now after adding the negative feedback, if I am calculating my sensitivity, it comes up as 1 upon 1 plus gh. Now for g and h to be positive values, you get 1 upon 1 plus gh. Okay, so 1 upon 1 plus gh is less than 1. So after adding the negative feedback, with negative feedback in closed loop control system, the system sensitivity to the parameter variations will decrease. Okay, as the original sensitivity in open loop system was 1, and now after adding the negative feedback, the sensitivity is less than 1, and hence the answer is that the sensitivity to parameter variations decreases. Let us see problem number 3, wherein we have asked that 3 blocks G1, G2 and G3 are connected in some fashion such that the overall transfer function is G1 plus G3 into in bracket 1 plus G1 G2 divided by 1 plus G1 G2. As you can see, we have to find out in what manner the blocks are connected. As you can see, there are 3 blocks, G1, G2 and G3. Okay. Now what we will do is, we will separate the fraction as G1 upon 1 plus G1 G2 plus G3 upon 1 plus G1 G2 and divided by 1 plus G2. Now these two brackets will cancel and we will be left with only G3. Now let us look at this function, G1 upon 1 plus G1 G2 plus G3. Now as you know, for a closed loop system with forward path G1, forward path gain G1 and feedback from G2, we will have this kind of transfer function, and we have the addition of G3 into system. Let us find out which option validates this particular conclusion. So option A is G1 and G2 with negative feedback and combination in parallel with G3. Yes, so this option A looks correct, because if we have blocks G1 and G2 in negative feedback and the combination of them with G3 in parallel, which will give us such a transfer function. Let us find out all the transfer functions for these and validate them. So for option B, we have G1 and G3 with negative feedback and G2 in parallel. So we will have G1 upon 1 plus G1 G3 plus G2, which does not satisfy our given function. Similarly, in option C, we have G1 G2 in cascade and combination in parallel with G3, which will give us G1 into G2 because they are in cascade plus G3, which does not also validate the given function. Okay. Option D, we have G1 and G3 in cascade and combination in parallel with G2. So even option D is not correct. So our first option A is correct in problem 3. Let us see what is problem 4. So in regeneration feedback, the transfer function is given by the catch here is you should know what is the meaning of regeneration feedback. Okay, so regeneration feedback means positive feedback. Okay, similarly you have degeneration feedback also. Degeneration or degenerative feedback, okay, which is nothing but negative feedback. So this problem solely suffices for the meaning of regeneration feedback. If you know the meaning of regeneration feedback, you will be able to solve this problem very easily. If you are not able to solve this problem, means you do not know the meaning of regeneration feedback. So regeneration feedback means positive feedback, and that is why we know for any transfer function with the positive feedback. So if you have g, y and feedback through h given positively in the summation fund, you will have, let us call this c of s and let us call this r of s. So you have c of s upon r of s is equal to g divided by 1 minus gh. Note this sign minus for positive feedback. Okay, for negative feedback we have plus sign here. So let us find out the option for this. So option D is correct in this particular problem. Okay, now let us go forward and see next particular topic and problems related to that. Signal flow graphs. So we have problem number 1 as the overall closed loop transfer function C of s upon R of s represented in this figure will be. Now this problem is given as a block diagram. You can solve this problem as a block and as well as through signal flow graph. Let us try to solve this problem from the block diagram reduction, which looks simpler here. As we have hinted a solution, okay, it is given that the solution is A, but we are more interested in how we have got to the solution. It is given that C of s upon R of s in this case is g upon 1 plus g. What is this g? G is nothing but the overall transfer function in this section. Okay, so of course if this block is represented as g, we have a unity feedback, negative feedback going towards R of s, and that is why we have the solution as g upon 1 plus g. Now let us find out what is g. So we have blocks g1 and g2 connected in parallel. Okay, so if you reduce them, they are in parallel g1 plus g2, and the negative feedback is taken up from the response of the output of g1 and g2 parallel. So let us first calculate the transfer function for this particular combination. Okay, so we have the transfer function for this blue circular area as g1 and g2 in parallel combined with negative feedback, that is g1 plus g2 into h2. Okay, so this is the transfer function for the blue part. Now this combination is connected in cascade with g3, and so we will multiply this particular transfer function by g3. Okay, and this is nothing but our g. Now we have our solution as g upon 1 plus g. Now just let us put the value of g into this particular function. So we get C of s upon R of s is equal to, so we have g1 plus g2 into g3 divided by 1 plus g1 plus g2 into h2 divided by 1 plus again the same function. So we have into h3 divided by 1 plus g1 plus g2 into h2. Okay, so we do not have h3 over here, g3, sorry, this is g3. Okay, so if you solve this particular function, you multiply this value to this one, we will get, let me use another color, let me erase everything and use another color for this. So if you solve that, you will get g1 plus g2 into g3. The denominator of that function will vanish and you will be left with g1 plus g2 h1 plus g1 plus g2 into g3. Now if you take common from these two terms, the bracket g1 plus g2, you will be left with the denominator as g1 plus g2 into h1 plus g3. Okay, so this is the denominator and this is the numerator of the required transfer function, and this is similar to option A. Okay, as you can validate, the numerator and denominators are equal. So this is how you will solve this particular problem. Let us go forward and see problem number 2, wherein you see a signal flow graph and it is required to calculate C of s upon R of s for this system. Okay, let us find out. So we have a signal flow graph and we know the Mason's gain formula, that C of s upon R of s is nothing but summation k is equal to 1 and up to n pk delta k whole divided by delta. Okay, so what is pk? Pk is nothing but forward path, kth forward path. Delta k is delta related to pk, and then you have delta is equal to 1 minus in multiplication of individual product of individual loops okay plus 2 non-touching loop products and so on. So you understand what is pk, delta k and delta now. So let us find out what is pk in this case, or what are the different forward paths in this case. So by looking at this particular diagram, you see there are two forward paths going from R of s to C of s. Okay, in a forward path you should not travel one node more than once, and you should travel in only one direction from R of s to C of s. So we go from this gain 1, then g1, g2 and 1 again. So this is our first forward path whose gain is 1 into G1 into G2 into 1, which is G1 into G2. And another forward path is you go from R of S 1, then G3, then go to G2 and then 1. So we have these two different forward paths. The gain in the second forward path is G3 into G2. Okay. So you have G3 into G2. Now, what are different feedback loops? Okay. Let me write what are different feedback loops. Feedback loops. Let us find out individual feedback loops now. So we have feedback loop that a point or a path which goes through a particular point and comes back that at that point again without traversing any other point more than once. So you have feedback going from G1, G2, and then you come back through minus H1. Okay, so you have one feedback path as G1, G2, and H1 with minus sign. Then you have another forward path through another feedback path from G3 towards G2 and coming back from H1 to that node again. So you have two different feedback loops. So second feedback loop is G3, G2 and H1 with minus sign. Again you have a forward path at this particular node. You have that forward path going from that point with gain G4 and coming at that point without traversing any other nodes. So you have the feedback gain as G4. Okay. So you have G4 as a feedback node. Please do not confuse G4 to be considered in any forward path. Okay. For a forward path, if you go from 1, G1, G2 through G4 and then 1, it will not be a forward path because while you reach from G2 to this particular node, say this node to be node A, and then again go through G4 and come back at A. So node A will be traversed more than once and hence it should not be considered, G4 should not be considered in a forward path. It is a feedback. So G4 is in feedback. Now let us write on the top what are our forward paths G1 and G2. Then we have G3 and G2 as PK and loops, feedback loops as minus G1, G2, H1. Then we have minus G3, G2, H1. Then we have G4. These are our loops. Let me erase we just use the eraser. Okay. Let us write the forward paths again. So my forward paths are G1, G2 and another forward path is G3, G2 and we have loops as G1, G2, H1 with minus sign. And we have G3, G2, H1 with minus sign and then we have G4. So these are our loops. Now let us find out C of S upon R of S with the Mason's gain formula. So we have Pk into delta K. So we have two different forward paths. Okay. So first forward path we have G1 into G2 and delta K is nothing but 1 minus the multiplication of non-touching loops to this particular forward path. So we have G1 and G1 G2 as our forward path. Let us find out which is the non-touching loop to this G1 G2. There is no loop, okay, there is no loop which does not touch G1 G2. Does not touch means they do not have any common node. G1 G2, so we have point G1 G2 here, so this is not touching loop for G1 and G2. Then again you have point G2 here, so this again touches PK or P1. Then you have G4, okay. So G4 goes through this particular node, and the path is 1 G1 G2 and towards 1. So G4 also touches G1 G2, okay. So no loop is there which does not touch the first forward path, so we will have 0 in this particular section, and we will have another forward path. So because this is summation, we have G3 G2, and again both all these loops do not touch G3 G2 as well, so we will have 1 minus 0 again, and the division will be delta. Delta is nothing but 1 minus multiplication or product of all the loops, okay. So you will have the multiplication of all the loops as okay, and then plus sign and the addition or summation of products of two non-touching loops each. So there are no two non-touching loops, because let us find out the first loop G1 G2 H1, G1 G2 and H1, and the other loops are G3 G2 H1 and G4. So both these loops have common nodes, and all these loops do have common nodes with each other, and there are no two non-touching loops, and therefore this should be 0, and hence my C of S upon R of S is G1 G2 plus G3 G2 divided by 1 minus G1 G2 H1. So we have sum of loop gains of all individual loops. Sorry, I should be writing the summation of all these loops over here. Okay, so this is not a multiplication. So we have summation over here, and so if I nullify the negative sign with negative sign, I'll write positive sign here. Write positive sign for the loop G3, G2 and H, and write negative sign for G4. So this is my C of S upon R of S for the given function. Okay, so this is my problem. This was not asked in GATE examination. This was asked in IES exam. Okay, so this is a little descriptive problem. Okay, and so you will not get such a descriptive problem in GATE, of course. Let us go towards problem number 3. Okay, you again have another block. Okay, now let us find out let us convert this particular block into a signal flow graph first. Okay, so what is the signal flow graph for this particular transfer function or the block diagram is, so you have R of S and you have a node. You go through G1 to another node, and you travel to another node through G2, and then you have your output Y. Okay, and now you have paths coming back from G2 to the middle point. Let us name these nodes as A, B, C. Okay, you have path coming back from C to B with H2 plus H2. Then you have path going from this particular value to point A. Do not confuse that you have a feedback from this point itself. No, you do not have a feedback from this point. Rather, you have a feedback from G2 traversing towards this particular node, and that is with H1 multiplied by H2. Okay, so this is how you will design your signal flow graph. Let us give the arrows. Okay, so I hope you have understood the transformation of this particular block to this particular signal flow graph. This particular arrow that you see from midpoint of H1 and H2 going towards the node B is a little confusing. This, if you just ignore the arrow over here which is going in this direction, this is the feedback to this particular node. So we have included this arrow towards B, but we have signal going from output Y traversing H2, H1 and going towards node A. So we have covered this particular path and the loop gain is H1, H2, or the loop value is H1, H2. Now let us write down the transfer function from Mason's gain formula. So you will have the forward path. So there is only one forward path here, G1, G2. So we will have G1 into G2, and there are no non-touching loops to this particular path, and hence the value ahead will be 1 divided by delta. Delta is nothing but 1 minus sum of all the individual loops. Okay, so what are the individual loops we have? G2 into H2, and then we have G1, G2 and H1, H2. Okay, minus G1, G2, H1, H2. So this is our answer for this particular problem. Okay, so this is the option G1, G2, G2, H2. Yes, the option C is correct in this case. Okay, I hope you have understood this problem. This was a little tricky problem. Okay, let us go forward and see solve problem 4. This is a simple problem. What are the forward paths given in this problem? So we have node x1 and x2 only, and only one forward path, T into 1, 2, and there is one feedback. There is no arrow. I'll give the arrow. So this is the arrow. Okay, this arrow goes from x2 and traverses the gain T22 and comes back towards x2. So this particular loop touches T12 and hence the values ahead will be 1. We will have delta is equal to 1 minus sum of all individual loops. So this is the one feedback loop T22. So we will have 1 minus T22. Okay, so this is a very simple problem. In this case, the option is A, T12 divided by 1 minus T22. So this is the answer for this question. Okay, let us go forward and solve problem number 5, wherein we have the signal flow graph as given, and we have some of the statements related to this particular signal flow graph. We have that consider the following statements regarding the signal flow graph. Statement number 1, there are 3 forward paths. Let us validate if there are 3 forward paths. So look at the arrows. So first forward path is certain in the straight line, traversing from B3, B8, B9 and B10. B3, B8, B9 and B10. Okay, so one forward path straight. Then you have arrows going from Z2 and directly at B8. Okay, Z2 to B8 and going further towards B9. Okay, and then B10. So you have another forward path 1, this 1 again is 1 into B9 and B10. So you have B9 into B10 as a forward path, and then you have a path going from Z2 directly at B9, and then you have again B10. So you will have B10 as again for the third forward path. So you have 3 forward paths. There are no other forward paths. So this statement is correct. Okay. Then the second statement is there are 3 individual loops. Let us validate if there are 3 individual loops. So let us see. We have B3, B2 and then B1. So this is first loop. Then you have the path going from B4 to B8 and then coming back to B4 through B5. So you will have this second individual loop. Also you have this path and the path going in this direction. Okay. So this is again one of the feedback path. So, and this is not considered in this case. So this is the third feedback loop we have. Maybe there are 3 individual loops and you can see the 4th loop over here. Okay, so this statement is wrong. There are 4 individual loops. Okay, there are no more than 4 individual loops though. Okay, this path already covers this particular node, say node A, and this B1 feedback path again will cover the node A, and that's why this is not a feedback path, another feedback path. Okay, so we have 4 individual loops. Statement 3 means there are 2 non-touching loops. Okay, we have 4 individual loops and we have to see if there are 2 non-touching loops. So this loop does not touch the loop 1, does not touch loop 2, and also does not touch loop 3. So there are 3 non-touching loops individually. Okay, but at the same time you will not have 3 different non-touching loops. So at the same time you'll just have 2 non-touching loops, that is either loop 1 and 4, loop 2 and 4, and loop 3 and 4, the set of 2. So hence there are 2 non-touching loops at any time. So this statement is actually correct and not wrong. Okay, and that is why you have statements 1 and 3 to be correct, and hence option D is right. Okay, let us move forward towards transient response now. Let us solve problems related to transient response. Assuming the transient response of a second order system to be given by C of t is equal to 1 minus e raised to minus 4t divided by root of 1 minus sigma square sine in bracket omega n into root of 1 minus sigma square plus theta. As you know, this is nothing but omega t. Okay, and we have to find out the settling time for 5% tolerance criteria. So that means the question asks, so basically this is the second order transient response for the system, for any system. So this is how my system is behaving. Okay, and now I want to calculate the settling time Ts, the time after which the value will settle down in the 5% tolerance band. Okay, so according to the formula, for 5% tolerance criteria of settling time, you have Ts is equal to 3 into tau for 5% criteria, and this is equal to 4 tau for 2% criteria. So we have to calculate for 5% criteria. So what is tau? Tau is nothing but zeta omega n, or in this case sigma. And we know that in C of t we have this e raised to minus 4t, which is nothing but e raised to minus zeta omega n t. Okay, so in this case, which is given as minus 4t, and hence zeta omega n is equal to 4. Okay, if you compare the values, you will get zeta omega n is equal to 4, and that is why tau is equal to 4, and hence, sorry, zeta omega n is not tau, tau is equal to 1 upon zeta omega n. Okay, so tau is 1 upon zeta omega n, so omega n is 4, hence tau is 1 by 4, and the settling time will be 3 into tau, which will be 3 by 4 seconds. So remember the units is in seconds, so you have option B to be correct. Okay, this was asked in IES examination in electronics. Okay, let us move forward to the problem number 2, which asks, a second order control system is defined by the following differential equation as given. Okay, the damping ratio and natural frequency for the system are respectively. Now, for a standard second order system, we have function as k into omega n square upon s square plus 2 zeta omega n s plus omega n square. Okay, so this is the standard second order transfer function, and we need to calculate omega n and zeta. Okay, so we have to calculate the damping ratio zeta and omega n also. Let us find out the second order transfer function from the given differential equation. If you take the Laplace transform for the double differential equation, you get s square. For single differential, you get s, and this is how you will get the Laplace transform as follows: 4 into s square plus 8 into s plus 16 whole multiplied by c of s. C of t is converted as c of s is equal to 16 into u of s. Our transfer function will be c of s upon u of s, which will give us 16 divided by 4s square plus 8s plus 16. Now to convert this into a standard form, you need to convert the coefficient of s square as 1. Okay, here coefficient is 4. So dividing numerator and denominator by 4, you get 4 divided by s square plus 2s plus 4. Okay, now this value is nothing but omega n square. Hence, my omega n square is 4, and therefore omega n is equal to 2. Right? Comparing the coefficient of s in the denominator, you have 2 zeta omega n is equal to 2. Okay, therefore you have zeta into omega n, which is 2, is equal to 1, and therefore zeta is equal to 0.5, which is nothing but damping ratio. So you have omega n is equal to 2 and zeta is equal to 0.5, which is given in option B. Okay, so option B is right. Let us go towards problem number 3. For the control system as given to be critically damped, the value of k required will be. Now again, for system to be critically damped, you need zeta is equal to 1. Okay, this is the requirement for critically damped system. Now let us find out the transfer function for this particular block diagram. these are in cascade, so you will have G is equal to 2k upon s square plus 7s plus 2, and h is equal to 1, and hence the closed loop transfer function will be G upon 1 plus G, which will be 2k divided by s square plus 7s plus 2 divided by 1 plus 2k upon s square plus 7s plus 2. So if you solve this, you get G upon 1 plus gh is equal to 2k upon s square plus 7s plus 2k plus 2. Okay, to this. Okay, now if we compare this with the standard second order transfer function, you will get s square plus 7s plus, sorry, 2 zeta omega n s. Let me write it again. Okay, so you get s square plus 2 zeta omega n s plus omega n square. From these equations, you get 2 zeta omega n is equal to 7, and you get omega n square is equal to 2k plus 1. Okay, now you have to find out the value of omega n to get the value of 2k plus 1. So you have zeta is equal to 1 for critically damped system. Putting zeta is equal to 1, you get omega n is equal to 3.5, and hence omega n square will be is equal to 12.25. Now you have omega n square is equal to 2 into in bracket k plus 1, and hence you have 2k plus 1 is equal to omega n square, which is 12.25, and hence if you solve this, you get k is equal to 5.125. Okay, so this is my answer. Here option B is correct. Problem number 4. Here consider a unit feedback control system shown in the given figure. The ratio of the time constants of the open loop response to the closed loop response will be. So the open loop response is 2 upon s plus 4. So this is my open loop response, open loop impulse response, 2 upon s plus 4. Now a standard first order system which looks like k upon 1 plus s tau. This tau is nothing but time constant, but for that the constant term should be 1. Here constant term is 4, so we will divide numerator and denominator by 4. Converting this into such format, you get 0.5 divided by 0.25 s plus 1, and hence the time constant for open loop is 0.25. Okay, or 1 by 4 for open loop. Now for the closed loop, you have negative feedback, unity feedback, and let us calculate the transfer function for the closed loop, which is 2 upon s plus 4 divided by 1 plus 2 upon s plus 4, which is nothing but 2 upon s plus 6. Now again, if you convert this closed loop transfer function into standard k upon 1 plus s tau, you get 1 by 3 divided by 1 by 6s plus 1, and hence time constant t2 is 1 by 6. Okay, for closed loop 1 by 6 is the time constant for closed loop, and we need to calculate the ratio of time constants of open loop response to closed loop response. So you have 1 by 4 divided by 1 by 6, which is nothing but 6 by 4 is to 2. So this is the required ratio. So option C is correct in this case. Let us solve. A first order system is shown in the given figure. Its time response to a unit step input is given by. Now you have first order system and which is subjected to a unit step input. So R of S is nothing but U of t, and whose Laplace transform is 1 by S. To calculate the response, you will have to multiply the transfer function of the system and the excitation. So you will have response is equal to 1 upon S into 1 upon 1 plus St. Okay, and now we have to calculate the time response for this particular function. Let us solve this and take its inverse Laplace transform. To solve this particular equation, we will first divide the numerator and denominator of the this particular bracket by t. So we will get 1 by s 1 by t upon 1 by t plus s. Now I have to express this particular function as 1 upon t, some constant upon s, and some constant b upon s plus 1 by tau. Okay, why I am doing this is because I can easily take out the inverse Laplace transform of this function and inverse Laplace transform of this function, which will be into e raised to minus t by tau, and in this case this would be a into u of t. So this would be my response. Now my task is to find out values of a and b. Let us find out the values of a and b. So you have a function as 1 by t 1 upon s into 1 upon s plus 1 upon t. Now to convert this into a by s plus b upon s plus 1 by tau, there is a trick. Okay, to find out a, which is over s, let us find out the critical value of this function at which value the denominator goes to 0. So at s is equal to 0, 1 by s goes to infinity, or say s goes to 0. So putting s is equal to 0 in the second bracket, you get s is equal to 0 and you get t. Okay, so value of a is calculated as putting s is equal to 0 in the function given. Okay, ignoring 1 by s and ignoring this constant for now because it is already present outside. If you put s is equal to 0, which is critical value of the first function, first multiply, you get t, and hence a is equal to t. Okay, again, so I'll just write over this a is equal to t. Now I have to find out b. To find out b, I will put the critical value of denominator of this function, which is minus 1 by t. At s is equal to minus 1 by t, this denominator will vanish, and hence putting s is equal to minus 1 by t in this particular function, you get minus t. Okay, 1 upon, so if you put s is equal to minus 1 upon t, you get minus t, hence b is equal to minus b. So you have the transfer function as t upon s minus t upon s plus 1 upon t. Okay, if you multiply these two functions by 1 upon t, you get 1 upon s minus 1 upon s plus 1 by t, and hence you have your time response as inverse Laplace of 1 by s is nothing but 1. Okay, and the inverse Laplace of 1 upon s plus 1 by t is minus sign as it is e raised to minus t into 1 by t, which is this. Okay, so this is my time response for the given function, which is given in option C. Okay, so option C is correct. Let us solve what is the unit step response of a unity feedback control system having forward path transfer function as follows. So you have this function. Okay, now I have to calculate the unit step response of a unity feedback control system like this. Now let us calculate the feedback transfer function. So if you have this GS and it is fed back with unity feedback, you will have G upon 1 plus G, which will be 80 divided by 1 plus and divided by S. If you solve this, you will get 80 divided by S square plus 18S plus 80. Now I have to find out if my particular function is overdamped, critically damped, underdamped or undamped. Now we will solve. We will have to find out the value of zeta for that. Okay, if zeta is greater than 1, the system will be overdamped. Okay, for zeta to be equal to 1, I will have critically damped system, and if zeta is less than 1, I will have underdamped system. Okay, so I do have function as 80 upon s square plus 18s plus 80. Now let us compare this with omega n square upon s square plus 18s plus 80, where this is nothing but omega n square. Therefore omega n is equal to root of 80, which is equal to almost 9. Okay, or less than 8.99. Okay, now we have 18 is equal to 2 zeta omega n. Okay, and omega n is close to 9. Okay, so if omega n is equal to 9, we get zeta to be equal to 1 for omega n is equal to 9. But actually the value of omega is less than 9, root of 80, and hence for omega to be less than 9, you will get zeta to be greater than 1. Okay, so zeta is approximately is equal to 1, but it is greater than 1, slightly greater than 1, and hence the system will be overdamped. Okay, so there is the catch here. System looks like it is critically damped, but it is overdamped because zeta is greater than 1. Okay, so here we will end our problem session. We have seen problems related to feedback principles, problems related to signal flow graphs and transient response. Thank you so much.